Tatsunori Hashimoto is an assistant professor in the computer science department at Stanford University. His research leverages tools from statistics to improve the reliability and trustworthiness of machine learning systems, especially in complex systems such as large language models. He aims to use robustness and worst-case performance as key perspectives to better understand and address some of the major challenges in machine learning and NLP. Before becoming a faculty member at Stanford, he was a postdoc researcher there, focusing on the trade-off between the average and worst-case performance of machine learning models. Prior to his postdoc, he studied at graduate student at MIT, and he was an undergrad at Harvard in statistical math.
Thank you very much. And thank you all for the attention. It's nice to be back. Hopefully the AV is, or sorry, the mic is working well for you all. Let me know if it's not. So in the lunch meeting today, someone asked me, why is it titled Back to the Future? Hopefully that'll become apparent in a moment here. I'm sort of excited about sort of this question of data efficiency for language models. So let me set the stage a little bit. I think if you've been working or thinking about language modeling, you've probably been thinking about compute as the key object of the last few years. And I think this is for a good reason. Growth in computational capacity and using compute scaling in various ways is what has driven progress over the last few years. And I think this is very much undeniable if we look at the sources of sort of the broad gains that we've had in language modeling, right? We've had pre-training compute scaling give significantly better base models. We've seen more recently compute scaling both at train and inference time with these reasoning models that give us really remarkable capabilities on tasks like math. And so in this sort of paradigm, the way you sort of think about things is compute efficiency. You say, OK, like, can I build algorithms that use the same amount of compute but give me better performance, right? Like, this is the game to play. But maybe in this talk, if you remember one thing, or at least one high-level thing, the thing that I want to try to get across is that maybe this is not the game that we will be playing in a few years. At least my contention is that compute scaling is sort of an anomaly in some ways. And the reason is because compute grows incredibly, incredibly fast. And it's very difficult for us to really grapple with the scale of compute build-outs and the scale of compute increases. But we see that, this is a chart on the right side here from Bill Dally talking about NVIDIA sort of compute growth. We have almost super exponential growth in compute year over year, right? This very, very rapid increase in not only just the total amount of compute, but the cost of compute has gone down. So of course, it means that if you believe that compute scaling is the only thing that matters, this is a great spot to be in, right? Capabilities will continually improve thanks to this super exponential. But I think one of the things to realize is that in all engineering problems, like if you have an abundance of one thing, your bottleneck shifts towards something else, right? So in our case, what will the bottleneck shift to? I would argue that it will be data, right? So on the left side here, this is a projection, I guess, when it was made by some folks, Epoch AI, who look at various sort of trends in AI. And they were looking at, OK, how fast does compute grow? How fast does data grow? What is the ratio of the two? And you see that compute growth in blue is quite rapid, whereas the growth in the amount of pre-training data or the internet data that we have available is much, much slower, right? Grows, I think, roughly 3% each year or something like this. And so if you compare these two numbers, you see that compute growth catches up very, very quickly to data. And that should either be concerning or exciting. And we kind of already see empirical evidence of these kinds of phenomena manifesting. We've seen sort of GPT 4.5 get released and then not make a particularly big splash. I like to highlight this line from OpenAI's own sort of technical report where they say, oh, GPT 4.5 is not a frontier model. And sort of I've added my own commentary, but it's 35 times more expensive, right? In his test of time talk, Ilya Sutskever said, OK, well, maybe it's the end of pre-training because compute is growing and data is not growing, right? In some ways, he has a way with words. This is the fossil fuel of AI, right? There's a finite amount, and we're perhaps exhausting. So all of this, I think, points towards the growing importance potentially of data relative to compute. And I was talking about this to some of my students, and some of the new students told me, oh, but don't worry. We have RL, and we have all these other things that will keep compute scaling going. And so I was compelled to add this sort of additional slide. And maybe you all are also of this view that, like, OK, Tatsu is old-fashioned, and he thinks about pre-training, and that's done and dusted. But don't worry, we have reinforcement learning. And to some extent, this might be true, right? I'm going to keep a little bit of an open mind here. And this talk will focus on pre-training. But I do think that these problems don't necessarily go away. There are other games that we could play that give us more data or different kinds of data. We could think about online feedback at scale. If you're OpenAI, you have a lot of users. Those users are providing to you either implicit or explicit feedback of various kinds. And that might scale very nicely. That's one possibility. More recently, you might think that the ability to use RL on things like math and code opens up ways of consuming tons and tons of compute on these settings. And of course, this is true. Like, you can dump tons of compute here. But really, I think the broader question here is that you need a source of supervision that either generalizes well enough or scales rapidly enough to keep up with the exponential increase in compute. And that's going to be hard no matter what your source of supervision is, right? So I'm going to focus on pre-training, but hopefully you sort of either appreciate or agree to some little extent that it's not going to be purely a compute game. We're going to have to think a lot about data and generalization and what I would call very classic machine learning concern. OK. So in some ways, at the beginning of this talk, I have framed this as being kind of this very new thing, right? Like, oh, compute scaling is the thing that's current, and now we will have something totally different. But I think the reason why I titled my talk Back to the Future is I think these concerns that I'm talking about, they are not new concerns. They are, in fact, a return to, I think, the classical foundations of machine learning, right? In kind of the pre-training and foundation models era, we have access to this gigantic corpus of data from the internet, this finite but very large amount. And so we maybe didn't have to think so much about data, the data greater than compute regime. But I think once we return to compute much greater than data, I mean, maybe much greater was a bit much for ImageNet, but I think a lot of the classic machine learning tasks that we might think about, things like CFAR or Penn Tree Bank or ImageNet or the 1 billion word benchmark, all of these tasks were really thinking about data constrained setting. Right? In these benchmarks, the game you would play is someone would hand you a finite set of data, a training data set, and you had to do as well as you could on some test set. So this is not a new game that we're going to be playing. It's a return to kind of the old ideas that we had before. So that might be both good or bad. And I think I forgot to say this at the beginning of the talk, but please do feel free to stop me for questions or comments or heckling as well. I'm very happy to take all three forms of commentary and feedback. OK. So that's kind of succinctly summarized here. I think there's going to be an interesting time where we get to do something pretty different from what we've been doing, at least in language modeling, for the last few years. I think the resource that's scarce is going to be changing over the next few years from compute to data. And that's going to change the nature of optimal algorithms and the kinds of research that we do. Like, how do we advance language modeling? Well, we might need to either fundamentally improve data efficiency or look for new forms of scalable supervision. And because I said that these are not new concerns, right, we have, in some sense, leg up on this problem. We can look to the past and use some really basic things that we learned in the past versions of machine learning and import those into language modeling land. And I would argue that those pay sort of immediate dividend. Going beyond that is going to be harder, and in some ways that'll be the kind of future theme. Like, hopefully, you all help advance that research again. So that's kind of the data constrained sort of story in the high-level picture. In some sense, that's maybe the most important thing that I'm trying to convey here, even more so than the individual research that I'm going to be talking about. But then, you might say, all right, so we're kind of done with this seminar, right? Like, we're done with, we know that data constraint is all we need. Let's just go read some, ImageNet papers. There are some things that I think are genuinely new from this new era of language modeling that I think we can use to think more clearly and more effectively about improving data efficiencies. So there's going to be two parts to this talk, and they're going to leverage two different tools when I do this. So in the first part of the talk, the one tool I'm going to use is using scaling laws. I'm going to try to embrace this idea of being able to extrapolate out model performance far beyond our training compute and use that as ways of reasoning about data efficiency sort of in the limit. In the second part, I'm going to think about synthetic data, which has been discussed ad nauseum broadly. But I'm going to do this in kind of the context of data augmentation. I'm going to think of synthetic data as a form of data augmentation. And if we embrace that, what kinds of algorithms do we kind of end up with? So that's going to be the two parts. I'm going to start with this very first part, which is really focused on the question of are there really simple things we can do? Just purely algorithmic interventions, no reasoning about language or the structure of our pre-training data set. And can we get really easy, straightforward wins for data efficiency? And this is a recent archive preprint we put out with Kongwu and Suhas and Percy called Pre-training under Infinite Compute. OK. I'll pause a moment here in case anyone has questions or comments about sort of the intro. Otherwise, I'm just going to keep going. OK. Good. So this very first part, I sort of laid out something maybe a little expansive in the title of the preprint there, pre-training under infinite compute, right? So what I'm trying to do is to be a little forward-looking and to imagine a very compute-rich future. That might be hard to believe because we're academics and we are very far from compute-rich, although I know you have potentially a few more GPUs than I do. But the exponential growth of compute means that I think this future is coming at the very least to the industry labs sooner than we think. And it might even come to us too if the cost of compute keeps falling. So I think the very first thing that we might start with is to say, OK, like in this compute-rich future, what do existing pre-training recipes for language models do, right? Like if we take what might be standard practice or even best practice, and we just apply it sort of naively but competently to our setting, what do we get? Well, I think the reasonable things to try is maybe we can just keep doing multiple passes over the data. That's pretty simple. And we can make models bigger, right? I think these have clear precedent in the current language modeling literature. There's a nice paper by Niklas Munninghoff and some folks, including some at Harvard here, on understanding repeated data. And Chinchilla and other papers have already argued that you can get better performance with less data if you scale up model size. But I think the unfortunate thing that we see is if we apply these very standard recipes of just repeating data or making models bigger, we really see that there's no benefit to compute past a certain point, right? That's kind of what this first plot is saying on the right here. It says I can do as many passes as I want, but at a certain point, I see overfitting, right? That's kind of what this is saying. And you should all expect this. This is machine learning 101. If you just keep training on your training set, you're eventually going to overfit. Same thing here on the left. If we have models that are bigger and bigger, benign overfitting is, of course, a thing. But at the very least, in our experimental setting, we don't necessarily see it. Even if we optimally tune learning rates and epoch counts, we see that losses eventually start going up if we have big enough models. So this is a kind of depressing state of affairs. It's kind of like someone came to you and said, I will give you infinite compute. And you said, well, actually, don't give me infinite compute. Just give me compute to do 8 epochs. So we're going to start with a very simple goal to start with. I'm not going to I'm not going to look for optimal algorithms under infinite compute. But I would like to at least do better than this, right? This is a non-monotonic curve as a function of compute. I would like for my performance to monotonically go down. And I would like for it to be somewhat efficient, right? So this is kind of the starting question. Is there a simple, purely algorithmic intervention that's going to make us scale cleanly, both monotonically and efficiently, with nearly infinite compute? So I think if we want to sort of engage with this question, of course, we could just start trying a bunch of algorithms. But I would like to do so a little bit more systematically. And so I think the 2 questions we might ask, number one, is what's the right way to do evaluation? Right? Like all empirical work depends on our ability to evaluate. So we should come up with a clean evaluation for understanding models in the infinite compute. And once we have that, what are good algorithms that can succeed under such evaluations? And to do this, we're going to, as I said before, look to the past to try to find some effective paradigms of doing so. Cool. So I think this is, in some ways, the biggest change from the leaderboarding things that have happened in the past. What we would ideally like to do is not just think about data constraints. We would like to think about data constraints absent compute constraints, right? So there's a difference between saying, in practice, we just have a lot of compute, so we don't worry about compute, and saying, I want to take the limit as compute goes to infinity, right? That one's a little bit different in what we're looking for. And so, I clearly don't have infinite compute. I clearly don't even have finite compute that can epoch, all of the internet. That's a lot of compute that I would need. And so what we're going to do is we're going to scale down everything, right? One of the things that I think we've learned over the last few years in pre-training is that if all you're looking at is pre-training losses, right, scaling is very predictable. You're able to scale down model sizes. You're able to scale down data sets. And if you see empirical regularities during scaling that sort of fit nicely, let's say in log-log space, then you can expect this potentially to hold for a few more orders of magnitude. And so what we're going to do is we're going to do a really aggressive scale down. And then under that very highly constrained world, we're going to try to derive optimal algorithm. And once we're done, we're going to scale that back up in the hopes that any insights that we found, transfer to sort of larger data set sizes and larger amounts. So that's going to be the general strategy. I think that's a strategy that's almost generically effective, regardless of the kinds of things we're studying. So to be specific, we're going to really scale down the world. We know that there's several hundred trillions of tokens of data available on the internet, but we're going to pretend there's only 200 million tokens that exist in the world. So we've very aggressively scaled that down. And the second thing we're going to do is that we're going to be willing to spend tons and tons of compute relative to that 200 million tokens. Right? We're going to be training 1+ billion parameter models on this data set. So that's going to be a lot of compute, way past sort of chinchilla optimal regimes. And then once we've done that, we're going to try to see whether there are sort of scaling laws that can be fit to this regime. And if there are, we're going to reason about algorithms not through their finite compute performance, but by taking the asymptotic limits of these scaling laws. Right? If we believe that these scaling laws are reasonable objects, this is a reasonable surrogate by which we can make algorithm development decisions. And then finally, as I was saying before, I don't want to stay in the small sample regime. And so I'm going to scale everything back up to 1.7 billion parameters. And we're going to look at the validity of any sort of algorithmic choices and conclusions we've drawn. Right? That's our attempt at a validation. Of course, we would like to scale up even further, but this kind of sets up a reasonable recipe for doing this kind of data efficiency work. Scale everything down, and then throw a lot of compute at that small world and scale it back up. Okay. Any questions so far? Good. So the first thing we have to do, now that I've sort of set up the game here, is that our baseline, which is just repeating the data and making it bigger, that doesn't even have monotone scaling, right? So we can't even reason about the asymptote of that object. And so the very, very first thing we do is we just have to do some hyperparameter tuning. And so we expand the space of allowed hyperparameters for language model pre-training. And really what we find is we have to basically apply very aggressive weight decay on top of these models. If you're a real strong believer in sort of a benign overfitting, you might believe, OK, we don't need any weight decay at all. It's all in modern pre-training, just an optimization assistance tool. We do find that in sort of very overparameterized regimes, weight decay that's very high, about 10 times higher than usual or more, is actually optimal and necessary to get smooth scaling like this. But once we've applied much stronger weight decay, and also I'll show in the next slide, much smaller batch sizes than is normal, we will end up with a nicely scaling scaling law. And not only that, the scaling law has significant improvements in losses under this data constraint regime. Yes?
Scaling law is based on the one.
That's right, the exponent, right?
Yeah.
Yes.
It is like the convergence for
That's right. Yeah. I mean, I think that's one of the things that we discussed quite a bit is why is that exponent so high? In chinchilla, that exponent, I think, is 0.2. Yeah, right. And so this is a much faster rate of convergence as a function of parameter size. I will say that the changes in the data distribution from other scaling law papers, where I think we're on DCLM here, could also be a factor. But I agree, could be. Right. I mean, you could think of it as local asymptotic normality or any of these asymptotic convergence arguments that would also give you 1 over n. I don't know if we're that far, because that would take a lot of compute and a lot of data to really get you to the quadratic minimum. Here, yes, that's right. That's right. We're doing an aspect ratio scaling. OK, good. OK, and so this gives us our first baseline for the asymptotic loss of 3.43. Notice that's much, much better than 3.75 that you would get with a standard recipe. And another thing I'll note is that this also means that a lot of the hyperparameters that you're used to is going to be different, and the system's concerns will also probably be pretty different. You find that the losses sort of monotonically improve with smaller and smaller batch sizes, because smaller batch sizes give you implicit regularization through the stochastic gradient noise. We find that bigger and bigger models require more and more stronger weight decay. And so we might actually end up in a very, very different hyperparameter regime as we end up in sort of more and more data constrained settings. And of course, smaller batch sizes poses serious challenges for parallelism. Okay, so that sets up our baseline, and the baseline is very boring. Like, I'm not hyping that up as some like deep insight here, right? We're just carefully tuning hyperparameters because that's important to get the empirics right. But we would like to go beyond that, right? So how can we improve data efficiencies? And of course, I think this is an entire sub area that has very rich things that we can do with it. But one of the things we wanted to start with was to establish strong baselines, right, in the infinite compute limit. And what do we think of as one of the most effective data constrained intervention? It's kind of ensembling, right? If you go to any of the classic leaderboards, like data constrained leaderboards from the past in machine learning, we see that ensembling is incredibly effective. I've taken just one screenshot of a modern version of this. This is from Harold Nikoloff in 2023, who are looking at Pentree Bank and Wikitext performance on various models. Like ensembles are way better than any of the models alone. And even if you just ensemble a single model with randomness, you get significant improvement. And so we look to the past, and this gives us some inspiration on what to do. And as a side note, I think one of the things that I'll say is, not only is this data efficiency thing rich, it also allows us to really leverage a lot of the lessons from the past. I think it's nice to see that what we've learned in the past actually does now help us improve models. So, okay, ensembles seem like reasonable things for us to work on. So what can we do? So this is like the V0 of an ensemble. And already, I would say that the results that we see are quite dramatic. Right? Ensembles add another way of spending compute. You can either make models bigger, you can epoch, or you can ensemble. Those are all different axes by which we can spend the compute budget that we have. And so now let's do the most simple kind of scaling possible. Right? So after we train one model, we can start having ensembles at 300 million parameters. I'm just going to, instead of having a 600 million parameter model, train two 300 million parameter models on ensemble. Right? And I can sort of repeat this. So every dot on this sort of turquoise or teal line, every dot there, that one is an ensemble of a 300 million parameter model. I'm just adding more ensemble members. And this kind of seems very silly. You might wonder, like, what kind of smart thing are we doing in the ensembling? All we're doing is we're randomizing the initialization and the data order, right? That's all that we're doing. And yet, despite the simplicity of this process, we're getting significant loss improvements relative to just making the model bigger. Oh, yes.
This K?
The K is the ensemble member count here. And the ensemble member count is proportional to the parameter count if you are thinking about like inference budget and so on, because it proportionally grows the total number. It only messes with the constant.
How many ensembles? So how many ensembles?
So that's a variable here on the teal axis, right? You can think of K as like a multiplier on 300. So each dot is a different K taken by taking more ensemble members.
They will train on the same data with same hyperparameter. Yes.
That's right. That's right. At least here, we're matching the hyperparameters. I'll talk a little bit about hyperparameter shenanigans in a bit. But OK, I mean, this is surprising and promising. I think as a kind of context side note, I think this project was born from us trying to do something very smart and sophisticated. Like originally, we were interested in data efficiencies for RL with like value functions and all these other crazy things. And then somewhere in the middle, we were like, oh, maybe we should try an ensemble. And the ensemble was so good that became the paper. And so, right, so that asymptote here is significantly better than what we saw before. And so now this kind of gets at David's questions, which is like, what's the hyperparameter? And this gets deeper into the nitty-gritty details. But I think the details are also kind of important because the gains you get from the details are significant. One of the things that we found pretty quickly is that the best hyperparameters for a single ensemble member, so look at this black dashed line on the rightmost panel over there. You see that the black dashed line has one scaling curve, and you see this like pink dashed line has another scaling curve, and they cross. The black dashed line is the optimal hyperparameter choice for a single ensemble member, so k equals 1. And pink is the optimal, I think, for the asymptote, right? So we've optimized for the asymptote of the scaling law. And they result in actually quite different hyperparameters. We need actually a lot less weight decay, and we want much higher epochs. And one way of thinking about this is if we're doing an ensemble, we're going to get regularization for free. And so we're allowed to overfit each of our ensemble members a little bit more and rely on the ensembling effects to kind of deal with the regularization components. And so the optimal regularization that we get through the ensemble is actually quite different. And so throughout sort of the rest of this part of this talk, what I'm going to do is I'm going to be optimizing for the asymptote of the ensemble through kind of this hyperparameter tuning process. OK, and now let's just kind of think about the ensemble here. I'm going to take the joint limit here. I'm going to take the ensemble count to infinity and the parameter count to infinity. The order I take this in doesn't really matter because we're in some utopia where compute is infinite. Bear with me for the moment here. So that allows us to basically take first the limit on the left. So each one of those lines is a different sized model. And I'm taking the ensemble member count to infinity. And then after we derive the asymptotes for each of those, I can fit a scaling law onto the asymptote. And somewhat surprisingly, the scaling law for this too is very stable. And we get sort of a secondary limit. And our estimate of this is that the double limit here gives even better asymptotic performance than the single limit that we saw before, where we just fix an arbitrary parameter size, and then we take the ensemble limit to infinity. In some ways, this shouldn't be necessarily surprising, right? Like if you have different ways that you can spend compute, you probably want to be spending infinite compute on every single one of them, rather than fixing one of them at some finite value. I will say that, of course, this taking double limits thing is really starting to read into the asymptotics of the scaling laws, and you should take this all with a grain of salt. We will do a little bit of validation later that will hopefully restore your confidence in this procedure. So now, assuming that you're OK with just looking at losses, pre-training losses, I think we have one remaining big question, or one remaining obvious criticism, which is that I am doing all these experiments on 200 million tokens. Right? And I'm drawing asymptotes and stuff, but that doesn't really change the fact that these data sets are tiny, right? And so I think a very basic validation that we now need to do is, does this thing work at bigger token budgets, right? Because really what we're trying to reason about is the behavior of algorithms at token budgets that are the size of the internet. And we are very, very, very far from that. And so the one thing that we can do is, once again, we can sort of take scaling laws very seriously and say, OK, what we're going to do is we're going to run the same experiment at different seed token counts. Right? We were at 209 million, but we're going to go all the way to 1.67 billion tokens. And we're going to do essentially the same tuning and all of these kinds of things, and then look at the scaling trends of the losses as we increase the seed token count under each of these recipes. So the minimum across epoching, remember that the standard recipe is not monotone, gives us this red line over here. The regularized asymptote, so this is the process of optimizing weight decay and so on, gives you this purple line over here. Notice that the gains that we got in losses, which are roughly the same as data efficiencies, you can think of them as kind of or a monotonically mapped object. They remain roughly the same as we increase the token budget by 8-fold, which is very encouraging. But now we have to reason about the ensemble. OK, so the question now, the real question is, does the data efficiency of the ensemble stay the same as we really increase the token budget? Of course, the answer is kind of yes, because otherwise I wouldn't be giving the talk. But the way in which we're going to take that limit and prove or try to give evidence for that is actually kind of tricky. And so I want to both tell you the procedure and the parts where potentially this gets dicey. So what's the issue here? The issue here is we have a triple limit that we want to reason about, right? I want to take the ensemble count to infinity. I want to take the parameter size to infinity. And I want my corpus size maybe not to be infinity, but to be large, right? Triple limits are kind of scary things. And I think you will see that we are going to do our best, but also there's going to be some dicey bits. So the first thing that we do is the same scaling limits as we took before. So for each model size, we're going to take the ensemble count to infinity. And that gives us one set of asymptotes to look at. Now, I'm going to repeat this. Now, I'm going to take a second model, the 300 million parameter models, and I'm going to look at the ensemble scaling. I'm going to look at their asymptotes, and that gives me the asymptotes for these parameter counts. And I do this for each one of my seed token sizes, which is sort of the shape of the plots over here. And I do this another 2 times. And that gives me essentially the scaling behavior as a function of the different corpus sizes, right? So now I have on the x-axis the model size for ensembles that are infinitely sized. And then I have different token counts for each of these kind of 4 lines. And so what does this give us? We can then read out essentially, you could look at the final point or the asymptotes really, but you can look at sort of the asymptotes of each of these lines. So each of these token lines, so what's the asymptote at 209 million tokens, 419 million, 838, 1.7, and that gives us sort of the estimates for the ensemble. So, I want to be kind of upfront, right? We're taking many sort of function fits and extrapolating this and so on. And so you should, once again, take this with a grain of salt. But I think the results are surprisingly clean. And I think this is consistent with a lot of the clean scalings that you see when you have very controlled hyperparameters and you're only looking at log loss for pre-training. And what you see is this sort of yellow line at the very bottom here. This is kind of the final scaling plot. This is, you have ensemble asymptotes. As we increase the seed token size, the data efficiency, which is the gap to these other 2 lines, roughly remains the same across different seed token sizes. And so even if you're kind of uncomfortable about sort of reading into the various asymptotes, right, even at sort of finite seed token count sizes, we can sort of demonstrate data efficiency improvement, right? Ensembles will get you performance that no models can ever reach at sort of, say, 1.67 billion tokens. OK, maybe I'll pause for a moment here. I feel like I've been rushing through a bunch of sort of asymptotic limits and so on. Oh, okay, let's see. Why did that disconnect? OK, hopefully that's back. I've been rushing through a bunch of limits. I'm happy to chat about any of this if people have questions. Yes. Yes.
Puzzle device. Suppose I just put through random Gaussian variable divided by 2.
Right. That's right. Well, this is parameter scaling, right? But yeah, I agree. This is faster than we expect. The 1 over n. But 1 over k and 1 over n is roughly the same thing, right? Like the k's are parameters in some ways. Or you're saying like it's faster than we expect for naive aggregation. Is that what you're saying? Yeah, I agree with that because we expect if it's purely a variance reduction effect around the minimum, then we would only expect 1 over root. We're ensembling the predictions at the softmax. We're not doing weight merging if that's what you're asking. We're not averaging the weights. We're ensembling we're taking a mixture if that makes sense. So this is the actual distribution. OK. Cool. But then I think my initial reaction to this set of results was, well, this is in some ways unsurprising because we're just getting bigger models. And even in a compute utopia, we still have to pay the bills on inference. And so this is maybe not a very practical thing to just ensemble things infinitely. So then we went down this road of trying to distill these back into single models. And we found 2 actually pretty intriguing results. One of them was that distillation does work, which means that data efficiency from this 8 ensemble, which is a very big model, can be baked back into a small model, right? So it's not like a data efficiency is fundamentally a property of larger or smaller models. The function class is rich enough to represent it, right? So this is the pink line. We took the 8 ensemble, and then we distilled it back into the original sort of 300 million parameter model. We retain the majority of the perplexity gains here. And in fact, it's better than you could ever do with this regularized recipe. It's lower than the asymptote over here. Right? So there's sort of gains from distillation that can't be gotten by just training for long. We also found another thing, which was really not our primary goal, but we found to be a really intriguing phenomenon, which is the self-distillation thing, which is the green star over here. So how you get this is you train a 300 million parameter model once. So you do one pass with like a reasonably tuned hyperparameter set. So you get that model. And now what you do is you train a second model on the output of that first model plus real data, right? And if you follow sort of this like data feedback loops or like model collapse literature, this might very much concern you because you're like, well, you're training the output of the model on a previous model, and that should be bad. But it turns out that actually self-training, there's been theory on this, is a form of light ensembling. And so actually you can get some of the gains of ensembling, or if not more, through just training on your own outputs. And that was a surprising result. It doesn't really neatly fit into some of the ensembling results, but it was a sufficiently strange result that I thought I had to mention it as part of the narrative of this talk. Yes? Yeah. Yeah, so I can tell you the sampling is unconditional, but I don't remember what the proportion is. I'd have to look back. Yes, sorry. The self-distillation? Yeah, I mean, the self-distillation is almost exactly as I said. Like, there's no not really bells and whistles other than like train model once, take outputs of the model, put it back into the model with real data. Yes, yes. There's really no advanced wrinkles in this scheme. It was very surprising to us for a long time. In fact, like additional context is we really started with self-distillation. We were doing a different project, and we found that we couldn't beat the self-distillation baseline. And we were like, what's going on? Like, how is this thing so good? And then I think it was either Komu or Suhas, like maybe it's just this, maybe it's just ensembling. And then the rest is this teal curve over here. Yes.
For the self-training, so for self-training, you actually trained on the model test.
Yeah.
Yeah.
Yes.
Like not the logits, but the.
Yes. That's right.
Yeah. Okay. So I'm wondering. So, in terms of implications for feedback loops and mode collapse, et cetera, those are not like power law phenomena, right?
Mm.
Those are very much not like monotonic even, right? So I don't, like, what do you think the implications are of the fact that self-training works in a data scarce regime, which I agree with like broadly across the, like, as you've been saying, that's something that, it worked in data scarce regimes in the past. No reason it wouldn't continue to, except that I don't know if you can like keep extrapolating, because that's something that.
Oh, yeah. So this, right, yeah. So I don't think you can like repeat this process and somehow like bootstrap up the, ensemble curve or something. Like that seems way too far of a stretch for me. But I do think like there is a definite N of 1 effect, and there might be other creative ways of getting ensemble-like effects that we might not be anticipating. Like maybe the one message I'll say here is like, I think when you think about self-training, you don't think of ensembling. So you're like, this is a bad idea. But actually, maybe there's like an ensembling story that makes it a good idea, at least for the N of 1 or one. Yes, sorry.
So the last one in here is just perplexity on like the data set you're training on.
Yes.
So if you do self-distillation, isn't that a approach to just optimizing for your source data?
Information theoretically, like you're right that like the objective is this, the population objectives are the same. You've gained no information. In principle, there's no new reason why this should work other than implicit regularization through ensemble style, potentially. Okay, good. Okay, and then the final two things I want to end on is, perplexity evaluations are good, but whenever you're doing something very different, you want to also make sure the gains transfer to downstream evaluations. And so, we took all of the different models we trained on the scaling law. So the left side shows, the various models we trained and the scaling laws associated with them. So parameter count versus losses. On the right side shows the equivalent average error across 3 different benchmarks that we picked because they read out really cleanly, at least in what we've seen on smaller scales. And so we see clearly very noisy stuff on the right. This is I think inevitable from downstream evals, but I think we see generally similar trends. The curves live in similarly different places. And I think maybe more importantly, ensembles sort of live in a Pareto dominant front, which I think is very encouraging if we want this to work for downstream. And then finally, there's kind of an obvious place to apply this, which is domain adaptation and continued pre-training. This will come up again in the second part of this talk. But there's kind of obvious gains that you can have by doing ensembles when you're doing continued pre-training on like mid-training data. So here we took like a math data set called OctoThinker, and we took their evaluations. So data efficient recipes like batch sizes and epoching like definitely help. So some of our learning transfer over, and we do see that K ensembles do significantly better. Of course, this is a setting where you can actually also even do model merging or like weight averaging. That works even better than the ensembles. I think of this more as a validation of the ensembling result rather than like this being the right way to do things. Of course, you want to probably do some model merge to reduce inference cost. Okay, so where I'm going to end with here on this first part is that there's potentially a looming data bottleneck. And it means, I think, maybe interesting changes in how we do research. Like maybe we can identify new sources of supervision that scale, or maybe we can do things like ensembling for inspiration. And I think the last thing, which I think is maybe more encouraging, is maybe we can look towards new sources of data efficiency, given that language models have sort of affordances that didn't exist in the past. So this is the second part, which is thinking a little bit about synthetic data. And this is two works with my collaborators like Zitong, Neil, Shuangping, Emmanuel, and also some Apple folks in the second one, Aonan, Honglu, Hong Wang, and Looming on synthetic data. So for this part, the thing I want to emphasize is that in some ways, there haven't been great developments, like broadly applicable great developments in algorithmic data efficiency, right? We know about regularization, but really that's been known since Tikhonov. Ensembling has been known, maybe since Laplace and Galton, depending on who you want to assign credit to. And so you might ask, like, is there anything new now that we have this language model stuff? And if not, you might be a little bit sad about, the potential outcome of this data constrained future. And I think one thing that gives me some hope that we can have a lot more data efficiency is that there are, we know about far more data efficient forms of learning than gradient descent, right? With GPT-3, we saw in-context learning that enables these like very, very few shot ways of generalizing. And so one way of thinking about data efficiency for language models is something like this chart, where we know that parametric learning is very, very scalable. You can process a lot of data, you can improve on some objective endlessly, but it's not very efficient few shot. We know that in-context learning is not particularly scalable. Like if you put in an infinite amount of data in context, that doesn't make your objective better and better and better. But it's got lots of few shot efficiency. So is there something at the middle that like we can hope for parametric sort of scalability and generalization, but also a few shot efficiency? And I really think of this as kind of the conceptual framework for how synthetic data and things might work. And so I've thought about synthetic data for a bit now, and I think it's a really interesting area, but also it poses, I would say, like pretty serious challenges in doing research. Because you kind of see that there's a critical threshold at which synthetic data stuff starts to work. One of my students in his rotation, tried to do these synthetic data things to basically generate and teach different models how to or teach different models basically a textbook using synthetic data. And what we found is that if you're using a 1B generator, this is this yellow line at the bottom, basically no matter what student model you use, you just see no gains at all. This model is just too bad at rephrasing to be able to see any sort of scaling gains. And so you need at least maybe like a 3B model to be able to see any sort of improving gains. And you also need a sufficiently big student model as well as a teacher model. So this makes scaling down very, very hard. I don't want to have to pre-train a 3B llama model every time I do a synthetic data experiment. And so this leads us to kind of a simple idea, which is to do continued pre-training instead of pre-training. And this, I think, provides like a really good experimental setting where we can study data efficiency without sort of burning tons of compute. So the setup is something like this. I'm going to assume that I have a pre-trained model F, and there's a small domain of knowledge that this model is not particularly good at. And my goal is going to be to come up with some set of training data set that when I train on it, allows this modified model to perform a range of tasks like QA or summarization or whatever on this setting. And of course, this is the classic problem of continued pre-training. But in some ways, this is also a really hard problem. A lot of the successes of continued pre-training is in very data-rich regimes, right? So things like tens of billions of tokens, like medical or code or whatever corpora. And so if we want to study data efficient approaches to language modeling, if we can do continued pre-training on 1.3 million or even less tokens, that gives us lots of hope that it's possible to use synthetic data to significantly improve the learning efficiency of our algorithms. And so let's say we take a collection of books, about 1.3 million tokens worth of books and articles and so on, and we have associated QA questions on those documents, and we sort of do some training. Well, it turns out that if we take a llama model, this black dashed line here, and we do continued pre-training on those documents, we actually get a model that's worse. Like no amount of hyperparameter tuning will get you above baseline performance. So that's this like green line over here. And this is kind of unsurprising. People know that continued pre-training doesn't work that well without tuning. But one thing that we do know is that we know pre-training works. And so what's the difference between pre-training and continued pre-training? I would say that it's the diversity of pre-training data, right? Like even if the two have the same facts, pre-training presents the same fact in many, many different ways. There's lots of different content. There's different style. And because of this, what we want to do is to try to essentially use a language model, take a book or some small domain of knowledge, augment it into a much larger set, and then train our language model normally on that. So our learning algorithm may be very data inefficient, but we basically dealt with that through this data augmentation step that allows us to essentially expand the data that we have. And this is very different from synthetic data for compute efficiency or for things like instruction. So in this setting, just rephrasing the data can kind of get you nice scaling gains. So this is the blue line over here. All I'm doing is paraphrasing the original articles and books, and I just generate a ton of synthetic tokens using that. I get nice predictable scaling up until a certain point where I beat GPT 3.5, but I can't really beat my teacher, which is GPT 4 in teal here. So that's good, but not really amazing. And so, what we thought of was that really the problem here, the reason why we can't, essentially generate more and more data and get more and more coverage is that language models are just not very diverse at generating synthetic data, right? When you ask it to paraphrase a document, there's only so many ways that it knows how to paraphrase or it's willing to paraphrase a document. So what we did was we sort of tried to inject external randomness by thinking about kind of knowledge graph style things. So what we do is we first prompt the language model for all the entities in a particular document, sort of enumerating kind of the vertices of a knowledge graph. We sample random subgraphs of this knowledge graph. So given a list of entities, we pick, let's say, 2 at random. And then we ask the language model to synthesize a relation between these 2 entities using the document provided, right? So as this example, let's say it's talking about 2 people, Lily and James, and various entities in the Louvre. And then the language model might say, oh, Da Vinci painted many works in the Louvre like Mona Lisa, right? And maybe that direct fact, that Da Vinci is in the Louvre, or works by Da Vinci is in the Louvre, that direct fact might not never be mentioned, but we've now synthesized and put that direct fact into the corpus, right? So we've taken implicit facts and turned them explicit and put them back in the data set. And this approach really allows you to continue scaling past a certain point. And scales very predictably and consistently way past GPT-4. We probably could have scaled out the rephrasing quite a bit more, but the scaling gap was sufficiently big that we sort of stopped it a little bit early because we wanted to see how far this pink line could go. Maybe more importantly, I think the fact that this is task agnostic rephrasing means that models trained with this way can generalize a lot like a language model could. So it can do summarization, it can reference facts that it's seen in various other contexts. And sort of weirdly, it was in some cases able to sort of compare and contrast different articles, even though we never put in cross-article training data. So that was a kind of interesting generalization, I guess, that it saw. When we try to summarize, we see that qualitatively, the model outputs from sort of this continued pre-trained model, which is at the top, produces a lot less hallucinations than the ones in the bottom. I've sort of taken the liberty of highlighting the hallucinations in red, since you don't know what the original text here was. And then finally, I think whenever I give this talk to more practically minded people, I think they start with the question of why would you ever do this? We have RAG systems, just put the facts in the context. And on the one hand, I agree. If you're practical today, you should put it in the context. But really, I think the interesting thing here is twofold. One is this maybe makes a path towards pre-training algorithms that pack more knowledge in, which I think is very exciting. But also, this opens the door to sort of specialist models that understand domains better and maybe complement RAG. And we see sort of some signs of that. So if we take Integraph CPT, which is on the left, and we add that with RAG, we see that the performance is better than just having a RAG. And it captures most of the gains or a significant amount of the gains going from base model to RAG, just doing this continued brief. OK, any questions before I get into the very last bit of talk? Oh, yes.
When you look at the hallucinations as momentary factually correct things within a longer, how do you actually automatically, do you automatically /how do you automatically identify the token by token inaccuracies in that?
Yeah, so the ones I highlighted, that was my student and I looked line by line and like claim by claim. In the paper, we have quantitative metrics. Those are generated by sort of like GPT-4 with reference. And we have like kind of the human agreement checks for that. OK, good. So then I think we were very encouraged by this. I think both Zitong and I got very excited about synthetic data. We said, OK, like maybe we can just augment our way to data efficiency. And so now I think this is the second work that I wanted to talk about, which is, can we now scale this up to pre-training scale and generalize things so we're not relying on sort of handcrafted prompt to do synthetic data? So the first one really is just a compute problem. Like we just need to train our own teacher. But the second one is a lot more subtle. Like what's a general purpose way to learn to augment data? And I think this is like another place where I would say sort of, we're looking back to the past. Kind of funnily enough, one of the first things I worked on in postdoc was trying to learn things like manifolds and local transformations of data in an unsupervised way. And one way you can do that is you can look at nearest neighbors of your data. And you can say, OK, like I've got a proximity function that's sane and gives me nearest neighbor pairings. I can learn a generative model that allows me to sort of move within my local neighborhood and use that to generate a bunch of data. So in some sense, the top summary is right, that I'm going to use nearest neighbors as a form of supervision to learn sort of data augmentation policy. Another way to view this is to say what we're going to do is we're going to build essentially a big nonparametric language model where we're retrieving random articles and we're learning to sort of smooth locally within a neighborhood. And I'm going to distill that back in to a bigger parametric language model. And sort of, it's kind of interesting to kind of look at all of these things as kind of inspirations for ways of learning how to generate synthetic data end to end. So this is all conceptually pretty simple. And I think the theory for this is also very well established. Like under certain regularity conditions, if you're looking at nearest neighbors and you fully model the local conditionals, you have an operator that you can use to traverse a manifold, right? And you can do random walks and so on. But actually implementing this is pretty hard, especially at pre-training scale. So one of the things that Zitong and our collaborators at Apple had to do was to scale up essentially nearest neighbor retrieval to the point where it could be applied at pre-training scale, both for the keys and queries, right? So this is not even like a RAG system. It's like for every document, I have to find all of the k nearest neighbors or neighborhood ball around them. And so we had to do a bunch of like quantization and sort of distributed search over the corpus. But once you have this like systems bit set up, conceptually, the remaining pieces to do sort of pre-training synthetic data generation is pretty simple. We start by just pairing up all the nearest neighbors using this fast approximate neighbor search. We learn the augmentation. So for each document, we use the neighbors as supervision for what kinds of data that we can generate. And that's our synthetic data generator. And then now I'm just going to sample from that conditional distribution to generate new synthetic data that I'm going to train on. So what do we get? So initially, we took a 3B parameter model with a 200 billion token budget. And we get models that scale quite nicely. So on the x-axis here, this is compute in billions of tokens. And on the y-axis is test loss. And once again, we're in a data constrained regime. So we are assuming access only to 10 billion tokens of real data. And so what we have is 75 billion tokens of synthetic data. And we have a bunch of repeats of the real data. And we see that the red line, which is our approach, eventually beats out, sort of repeating and regularizing the original. So this is the scaling of our method. And it's very close to the Oracle, which is basically getting fresh data all the time, which is kind of encouraging, at least up until this point. The gap is, unfortunately, however, growing. This got scaled up even further, not by us, but by collaborators at Apple. And at the 1 trillion token scale, basically the same trend holds. Like half the gains relative to the Oracle can be captured through synthetic data. So that's quite nice. It's not quite as good as having fresh data. We don't expect that to be true. But synthetic data is capturing a significant amount of the gain of getting fresh data relative to sort of repeating and regularizing better. Finally, one thing that is kind of encouraging is that in all of this case, what we're doing, right, is we're training our own teacher. So we first do pre-training to train our teacher model. And that teacher model synthesizes data, which then is used to improve the teacher once again. As the teacher model grows in scale, various sort of artifacts in the data, like the rate at which we have non-factual responses, which we judge with LM with web search, or pairs where the input to output is irrelevant or where it just copies, those rates generally go down. So the quality of the synthetic data seems to be improving with scale, which is encouraging if you think that sort of scaling this up should hopefully be giving you higher quality data as you go. So OK, so to put all that together, I think synthetic data is very interesting. In some ways, it's much like the classic sort of data augmentation idea that's always existed and works. But I think there are new affordances, right? Like the ability to sort of like build entailments or turn implicit facts into explicit facts. Those are very new sort of levers that we now have to pull, and we can design interesting algorithms with them. I think there's lots of sort of big, important open questions. Can we really completely close the gap between in-context learning and parametric learning? I don't know. And what are the limits to synthetic data-based augmentation? We've been thinking a lot about, now asymptotes to this process. Like if I keep generating synthetic data, can I eventually get, models that are good? And then finally, and the thing that seems most unclear to me is for facts, it seems really clear what kind of data we should be producing. For reasoning, I kind of have no idea what synthetic data means or even should look like. So I'll close here. Language modeling, I think, as I said before, we've been in a compute-bound regime thinking about flops and compute efficiencies and so on. But I'm hopeful that I think things are going to be a little bit different and maybe more interesting. We're going to think a lot about generalizing from limited data. We're going to think about a lot of the foundational statistical questions of the field. And I think there will be challenges because algorithmic gains have been really hard to gain, even in the deep learning era, and not really well understood. And so maybe we need new theories. But it's also a very exciting problem because I think, as machine learning people, I think we've been excited about this prospect of induction and learning from limited data and generalizing. And I think that's a really exciting thing to ask even for language models. So thank you very much.
It's idea to scale up the iteration.
Yeah. So the answer that I can give for you're talking about this, right? Yeah, the answer that I can give to that is that we didn't tune this very aggressively. Basically what we tried to do was we originally came up with a token budget, and we tried to make sure not to repeat synthetic data any number of times, and that sort of constrains the real data repeat rate. So we weren't tuning this, which hopefully means it's not too sensitive, but we're also not too sure. Yes.
One question on the knowledge graph application. Are you just doing first order gains?
Yeah, so we were doing kind of exhaustive sampling of K cliques. But given our token budget, realistically, what that means is we exhaustively enumerate all pairs, and we randomly sample some subset of 3 cliques. We do see if you stratify by the clique size, the higher order cliques have a lot less value. And so, if you were to press me on it, I would say that really the direct links are probably the most valuable, at least for this form of augmentation that we were exploring.
Then the follow-up question. How much of this is relying on missing links in data? And do you expect missing links in real data?
Yeah. I mean, I think at least conceptually, this is almost entirely relying on filling in missing links. That's kind of the reason why I think this is a safe and obvious bet. I do think in real data, missing links is pervasive, right? You don't state all of the implications of all the facts in your in your document. And I think things like the reversal curse is a great example of this, right? Even if you have facts, the reverse directionality is not, in the document. I think ideally you would, go to cross-document entailments and all of these things. And I think one of the motivations for doing this second approach, where we're basically trying to generate across documents, is to do exactly this kind of cross-document thing that would allow us to go beyond, singleton links in a single document.
Sweet. Let's thank our speaker one more time.